Welcome back, students. In this video segment, we're going to make a major shift or take a major shift in the course. We're going to begin Chapter 3. We're going to begin the study of differential equations. So in Chapters 3 and 4, we will look at differential equations, and then we'll return to Chapter 5. We'll return to vector spaces, including concepts of things like linear transformations. In fact, linear transformations are the big topic in Chapter 5. So let's get to Chapter 3. In this video segment, we're going to cover 3 sections. Don't panic too much. The first section is just an introductory section. It includes mostly a little bit of terminology. It's 3.2 and 3.3 where we really begin the course, the actual solving of differential equations. In Chapter 3, we primarily deal with what are called first-order differential equations when we do some second-order differential equations. So let's start by talking about a word I just used there, the order of a differential equation. In fact, let's be a little more basic and talk about what the definition of a differential equation is. A differential equation is nothing more than any equation that has one or more derivatives of a function in it. Okay, so if your equation has a derivative or 2 derivatives or 3 derivatives of a function in it, it's called a differential equation. So here's some examples. Differential equations. So differential equations. And if you want, you can abbreviate DE. So let's put the DE on this side. And on this side, let's put the order of the differential equation. The order of a differential equation is not difficult. Here's an example. So a differential equation might be y prime equals x. Y prime equals x. This equation has one or more derivatives in it of a function. It has one derivative specifically, so it's called a differential equation. This is a first-order differential equation. First-order differential equation. Okay, suppose we have another differential equation. Y prime equals the function y. This is a differential equation because it has one or more derivatives in it, and just like the other one or the previous one, this has one derivative in it, first derivative. It doesn't have to be the first derivative, by the way. It could have been y double prime equals y. It is a first order differential equation again. So if we have something like, let's say, y double prime equals y, we have a second order differential equation. If I add another prime on the right, y double prime equals y prime, I still have a second order differential equation. So I think you're getting the idea of what the order of a differential equation is. Suppose I have y double prime plus y equals 0. That's a second order differential equation. So the order of the differential equation is the highest order of derivative that's in the differential equation. So if the highest order derivative is 2, then whether or not the differential equation has any lower orders in it, namely the first derivative or the 0 derivative of the original function, it's called a second order differential equation. Differential equations are not always written with the prime notation. Of course, we could also write the last one given there is d squared y over dx squared plus y equals 0. These are of course they're the same differential equation. Okay, and they don't always have to be written with derivatives indicated. We could have a differential equation written in differential form. So if you had something like x squared plus y squared times dx plus 2y dy equals 0, this is still a differential equation, even though it doesn't appear to have any derivatives in it. It does if you divide both sides by dx. Remember, we're treating dy and dx as differentials. So if we divide both sides by dx, you have x squared plus y squared plus 2y times dy dx equals 0. So this is a first order differential equation since it has a y prime in it as the only derivative in it. Okay. In this course, we're primarily interested in, like almost 100%, primarily interested in the solutions to differential equations. And my statement there really is buried in that statement is something pretty big. We're not interested in the existence of solutions. We're going to assume that solutions exist. We're interested in actually the mechanics of finding the solutions to the differential equation, solution or solutions. Okay. So what is a solution? Well, a solution to a differential equation, the solution to a DE, differential equation, is any function that satisfies the differential equation. Is any function that satisfies the differential equation. Okay, so let's take a look at an example. Suppose we look at the differential equation y prime equals 2x. Okay, y equals x squared is a solution to the DE, to the differential equation. Why? It's not a solution because if we integrate both sides of the differential equation, we get x squared as one of the solutions. It's a solution because if we substitute the function x squared into the differential equation, it works. Okay, so again, if you missed that, y equals x squared is a solution to the differential equation since let's see, it it satisfies the differential equation. So what do I mean by satisfies the differential equation? So if y equals x squared, then y prime equals 2x. So that's what we mean by satisfying the differential equation. You notice that if y equals x squared, then y prime equals 2x. So the differential equation, the DE, was y prime equals 2x. So if you substitute the derivative into that, if you substitute the derivative into the differential equation, it works. Okay, so any function that when you substitute into the differential equation, it works, is called a solution. Now the thing is, this is not, of course, this is not the only solution. Y equals x squared plus 1, y equals x squared plus 2, y equals x squared minus pi over 6. You thought I was going to say x squared plus 3. These are all solutions. If you take their derivatives, you get 2x. Substitute into the differential equation, it works. Okay. An expression that gives you every solution is called the general solution. So y equals x squared plus a constant plus c is called the general solution. Very often we're interested in finding the general solution to a differential equation. To the differential equation. Very often we're looking for that solution, the most general solution. Okay, so next consider y prime equals y. Y prime equals y. Now, think about this differential equation. Just think about it. You're looking for a function. Obviously, y. You're looking, the function is y. Or a function is y. You're looking for a function y such that y prime equals y. You're looking for a function that when you take its derivative, you get the same function back. There's only one derivative. There's only one function in your universe that behaves that way. What is the only function you can imagine that when you take its derivative, you get back the same function. It's the exponential function. So that's a solution. Y equals e to the x is a solution. Now, I chose this differential equation on purpose because I don't want you to generalize what the structure of solution of the first differential equation, that is x squared plus a constant, x squared plus 1 plus 2 plus pi, minus pi over 6, etc., etc. I don't want you to assume that that automatically works. Y equals e to the x plus 1 is not a solution. Why? Well, let's see what happens. If y equals e to the x plus 1, y prime equals e to the x. Okay, the dE, the differential equation, was y prime equals y. So if you substitute e to the x plus 1 into the differential equation, you get e to the x on the left-hand side, and it has to equal y. You get e to the x plus 1 on the right-hand side, and this does not work. E to the x is not equal to e to the x plus 1. In fact, y equals e to the x plus c is not the general solution. Although the general solution does have an arbitrary constant in it. Okay, let's not go too fast past what I just said there. Y equals e to the x plus c is not the general solution. Why? Well, we saw that it doesn't work for c equals 1. So if it doesn't work for one case of c where c is supposed to be arbitrary, it's not the general solution. C has to be any arbitrary constant. And it's not easy. It's not difficult to check for the most general constant c that it doesn't work. Just take a derivative. You get e to the x for this function. The derivative constant is 0. So on the left-hand side, you substitute, you get e to the x for y prime. And on the right-hand side, you get e to the x plus c. So in fact, this won't be a general solution. It'll only work for c equals 0. So what does the general solution look like? So this is sort of an indication that there's more to finding the solution to differential equations than just adding a constant to a solution, or even integrating the both sides. You can't integrate both sides of this to get this differential equation to get the solution. Okay, close, but not quite. So the general solution, you're going to be able to see this, how to get this general solution in this video segment. The general solution is y equals a constant times e to the x. Okay, so why? Well, let's see what happens when you take a derivative. The derivative of c e to the x is c e to the x. So here's the dE. The dE is y prime equals y. So I want to see what happens if I substitute the solution into the differential equation. So y prime equals c e to the x. Okay, so there's y prime substituted in on the left-hand side. And that's supposed to equal y. So that's supposed to equal y, but y, substitute that into the right-hand side, equals c, oops, I don't want to keep red on there, equals, hang on a second, equals c e to the x. So definitely, this is true. This is true. We can take off the question mark. Okay, so a solution is any function that when substituted into the differential equation, it works. The general solution is the solution that contains all the solutions. Now there's a big question here. Why should it be that y equals c e to the x is all the solutions? Even with an arbitrary constant c, why can't it involve something else? That question is going to be left to the proof of that, of the answer to that question will be left for math majors. Math majors will very, very likely take this course over again, depending on whether you're a pure or applied math major. And then prove general results. Prove that this is a general solution. I haven't even proved that the solution to the one we just did was the general solution. It looks like it should be. For the previous differential equation, the previous differential equation looks like y equals x squared plus c is the general solution. Why can't there be something else? Why can't it be sine of x over x cubed plus 14 or whatever? I haven't proven that the solutions that I've given are exhaustive. That means I haven't proven that I found them all. Now, we won't have to prove that. This is not a course for math majors. This is primarily a course for applied science majors, STEM majors, non-mathematics STEM majors. Okay, so STEM without the STEM, without the M. So STEM majors. Sorry about the bad humor. Okay. There's another kind of problem that we address in this section, or in this chapter. Not in this chapter, in this course. They are called initial value problems. Initial value problems. Initial value problems contain two things. They contain a differential equation. Let's do this. A dE and some initial conditions. Some initial conditions. So for example, y prime equals 2x. There's a dE with y of 0 equals 1. Okay, so there's a dE plus an initial condition. Okay, it doesn't have to be a differential equation with one initial condition. You can have a differential equation with multiple initial conditions. For first order differential equations, as we'll see soon, generally we have one initial condition. For second order differential equations, we have two, and so forth. And what the initial value problem does is it zeroes in on a particular solution from the differential equation. So if you missed that, here's sort of a really quick example of what I just said. So the general solution to the differential equation is y equals x squared plus a constant. Y equals x squared plus a constant gives you a whole bunch of parabolas. They're just, whoops, I don't have to be too sloppy about this. Shouldn't be sloppy at all. A whole bunch of parabolas that are just shifted vertically from one another. That's all they are. Okay. But the solution to our initial value problem, the solution to the initial value problem, and yep, we're going to abbreviate initial value problem, IVP. The solution to the initial value problem is only one of these curves. It's only the one that passes through the point 0, 1. Okay, so our solution, let's see if I can do this. Our solution is going to be, I got one half red. The red one, as long as my surface is going to allow me to, oops, as long as my surface will allow me to color the left half of this red too. Oh, it may not. Oh, it's not gonna. Hold on. Oops. I think I'm making a mess out of this. I know how to fix this. I should have just done the simpler thing here. Watch. I guess you are watching. Just take that one off and then put on a red one, a red piece. There we are. Okay. All right. In any case, our solution is the one that passes through 0, 1. That is, our solution satisfies not only the differential equation, but the initial value. So initial value problem satisfies DE, and also satisfies the initial condition or conditions. Initial conditions or shuns. Okay. All right. You studied an initial value problem. Most likely you studied one, even if you haven't studied them in calculus-based physics. You studied one in probably in Calc 1. If you have a cliff and you got a person here that's going to drop an object off the cliff, I think the author of your textbook calls the positive y direction is downward. Yeah. Then and you're interested in the height of the ball or object or rock or whatever as a function of time. That height of the ball as a function of time is approximated very well by a solution to a differential equation. The acceleration due to gravity is a constant, let's say negative 32 feet per square second. Okay, it's a given constant, gravitational constant, as long as you're close to the surface of the Earth. And if this person were too far away from the surface of the Earth, he wouldn't be able to breathe. So we're going to assume that the acceleration is negative 32 approximately. And we have initial conditions. We have, if I put the positive y-axis down and start throwing this thing down or dropping this ball at 0, we have y of 0 equals 0. If the person just lets the ball go or the rock go without tossing it down or tossing it up and letting it come down, you have initial velocity of let's say 0. Okay. And this is an initial value problem. Why? Because acceleration is the second time derivative of position. Learn that in Calc 1. Real fundamental in physics. So acceleration, d squared y over dt squared is and in fact it should be positive 32 because we're putting the positive x-axis or y-axis down. So d squared y over dt squared is 32 with y of 0 equals 0, and the velocity is y prime. So y prime of 0 equals 0. Okay, and that is an initial value problem. A very common one. It's common. It's also not very realistic, because what's being ignored here, you physics types, what am I ignoring here when setting up this differential equation? I'm ignoring something very, 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 very important. And if you thought it or said it really good, it is wind resistance, friction. Okay, so without going into too much detail, it's very common to model wind resistance. So let's say wind resistance that is modeled by directly proportional to, so let's say minus b times velocity. So it's very common to model wind resistance as being directly proportional to either velocity or velocity raised to a small exponent, like 1.5 or 2. It's very, 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 very common. Okay. So if we were to adjust this differential equation, it would also contain the wind resistive factor or term. And again, velocity is dy dt, so it would also, the differential equation would also contain dy dt in it. I know I'm not going to set up that differential equation. I think we're going to look at it in 3.9 or something like that in a later section. I'm not going to do that here because that will require a little bit more. It's going to require for you physics types, if you've already taken or are taking physics, it's going to require a free body diagram and Newton's second law really to justify the differential equation a little bit more. Those of you who haven't had physics, don't worry about it. Don't worry about it. We'll cross that bridge when we get there. And I think it's like section 3.9. Might be 3.7. I can't remember. Okay. So there's not much to worry about with this first section, 3.1. Your author talks about existence of solutions and uniqueness of solutions. We're going to assume the existence of unique solutions because we're primarily interested in the mechanics of how to find solutions once we know they exist. So the homework for this section should take all of 10 minutes, 15 minutes tops. Where the course gets a little more involved is in the remainder of the course, the chapter. For us, let's take a look at sections 3.2 and 3.3. Let's take a look at some very elementary methods of solving a couple of first-order differential equations, types of first-order differential equations. Alrighty? Okay, so let's go ahead and consider separable differential equations. Separable differential equations. If your first-order differential equation, and again, this section or this particular section is for solving first-order differential equations or initial value problems involving first-order differential equations. Suppose our differential equation can be written in the form some function m of x times some other function n of y. Okay. This type of differential equation is called separable. The differential equation is dy dx equals one function of x times one function of y. So obviously, not every differential equation is of that form. So for example, a separable differential equation would be dy dx equals x squared plus 1 cosine y. Okay, so it's one function of x times one function of y, the derivative. So not separable would be dy dx equals, let's say, x squared plus y squared. The first differential equation has a solution that's not very difficult to find. The second one, the non-separable one, and get this, the second one has no simple solution available. It is impossible to solve this differential equation with using elementary functions or finite combinations of elementary functions. Elementary functions are the ones you grew up with, like powers, roots, rational functions, sines and cosines, logs, exponential functions, that sort of thing. You cannot solve that second one. If you want to challenge me, you can try, but don't take too much time away from homework for me. But it's very well known that this second one has no simple closed form for the solution. Okay, that's not to say that all non-separable differential equations have difficult solutions. That's not the case. It just happens that this very simple looking one doesn't. So let's look at a simple one that is separable, and let's solve it. Solve. Suppose I want to solve the differential equation dy dx equals one of the first ones we looked at. We already know the general solution is some constant e to the x, general constant e to the x. Let's show that. You can't get at the solution by just integrating both sides. Okay, so let's get that out of the way. It's wrong to try to integrate both sides. It's wrong to take dy dx equals y. Oops, that's an ugly integral sign. Dy dx is y, and integrate both sides with respect to x. Shouldn't say it's wrong. It just won't give us our solution, because look what happens. We get y, the antiderivative, most general antiderivative of the derivative is y plus a constant, equals the integral of y dx. Okay, I guess you can put plus a constant, although the integral of y will also already contain the constant. So that's really nice. This is I wrote wrong. Technically, what I've written there isn't wrong. It just doesn't give us our solution. We've replaced one problem, a differential equation, with another called an integral equation, which is a whole other story. We'll actually, if there's time, we'll actually solve some integral equations when we get to much later in the course. In fact, toward the end of the course, when we look at something called Laplace transforms, we're going to look at something called Volterra integral equations. But no, this is nice, and the mechanics of what I did are correct, but it doesn't give us our solution. So there has to be something else, and it's a simple something else. The idea is to separate the variables. So the correct thing to do is to separate variables. Separate variables. And by separate variables, I mean gather y's and dy's and dx's and dx's. So the original differential equation is dy dx equals y. Divide both sides by y. And multiply both sides by x, or dx rather. So we get dy over y equals 1 dx. And here's what makes this the simplest method of all. And then we just integrate both sides. With respect to the variable on each side, of course. And this is easily justifiable if you're a math major. You can easily justify this using the chain rule. Chain rule from Calc 1, but don't sweat it. Just separate the variables and integrate both sides. Okay? And be very, very careful with absolute values. Be very, very, very careful. Fair warning, if you're not careful with absolute values, it could be a very, very expensive point loss on tests. And from my point of view, even worse, it's very bad learning. I'm not so much concerned about your test scores as I am that you learn the material. But I know you're really concerned with test scores. I was too. So the integral of 1 over y with respect to y is the natural log of the absolute value of y, not the natural log of y. Not the natural log of y. So if you're taking notes as you do this, and you should be doing that, make note that the answer is not the integral of log of dy over y is not log of y. It's a log of absolute value of y. Now the integral of 1 with respect to x, the most general antiderivative of 1 is x plus a constant. So I'd like to solve for y. This, by the way, this form of the solution is called an implicit form of the solution. It is a form of the solution. The solution, that is the solution I just wrote. Log absolute y equals x plus c. That's perfectly legitimate as an implicit form. Implicit meaning that I haven't solved for y, the dependent variable, as a function of x. Or x is a function of y, but since it's given as a derivative of y, I'm assuming that y is a function of x. So an explicit solution we get by solving for y. And spoiler alert, you can't always solve for y. It's not always possible to find an explicit solution. Okay. More of that, I believe, coming up real soon. So suppose I want an explicit solution. Then I'll exponentiate. I'm going to take e to both sides. Remember from Calc 2, that's called exponentiation. Okay, and I'm going to use some algebra on this. So we have absolute value of y. Exponential and logarithm functions are inverses of one another, so they cancel each other out when you apply them, when you compose them together. And e to the x plus c is the same thing as e to the x times e to the c. Properties of exponents. So I'm going to write this with the e to the c first. So this is e to the c, e to the x. And remember from algebra, if you have absolute value of x equals, say, 5, then x equals plus or minus 5, just as a reminder. And the reason I'm reminding you of that is we need to get rid of the absolute values. So if the absolute value of something equals a positive quantity, and e to the c times e to the x is positive no matter what you choose for c or x, then y must be plus or minus e to the c times e to the x. Now what we can do is we can replace the plus or minus e to the c with a single constant k, or anything other than c. Y equals k e to the x, and that's the general solution. That's the general solution, and this is an explicit form of the, and I should have said general above, general solution. So of the above general solution. Implicit was above general solution. Okay. If I'm not explicit, no pun intended, but if I'm not explicit on a test, then an implicit solution would be fine. Now again, tune in very, very carefully to what I'm going to say in about 5 seconds. If I am explicit on a test, again, no pun intended, and I want an explicit solution, give it. Okay. Following directions for my exams is extremely, extremely important. You're being tested on the materials, but you're also being tested on whether you can follow directions like a good science major can. Okay. So anyways, that is how separating the variables works. Separation of variables works. Let's take a look at more examples. Let's take a look at, for example, solve dy dx equals a times y, where a is a scalar. Okay, very little difference here. This is a differential equation that models exponential growth or decay. So was the last one, but this is more general with the constant a in it. Okay, so do the same thing. Separate the variables, integrate both sides. So we get the natural log of the absolute value of y equals ax plus a constant. Solution goes very much the way it did before. Exponentiate, so we get e to the c, e to the ax. That's like a simplified version of e to the ax plus c. So y equals plus or minus e to the c, e to the ax. So y equals some constant e to the ax. Okay, very often, or rather this differential equation happens so often that a lot of students just memorize the solution. I would recommend it if you're a science major, which is most likely what you are. There are some computer science majors take this course for some reason. I don't get it. I'm happy to have you. Believe me, don't get me wrong. This class is mostly for engineers. It's mostly an advanced engineering math course. This differential equation happens so often that a lot of students memorize this, and I think a lot of physics instructors do too. I believe that. I seem to remember that. Okay, so here's a general solution, an explicit form of the general solution. So let's take a look at some more. Or oops, I'm gonna get out of red. Back to black. Example. Let's say, here we go. Oops, I guess I should give directions. Solve dy dx equals x e to the x minus y. X e to the x minus y. Okay. The way this sort of plays out on an exam is you're going to see multiple methods for solving different types of differential equations. And what you do is you search for a method that works. It goes very much the way in Calc 2 integration went. When you were integrating something, you had to search for the correct method. Integration by parts, partial fractions, powers of trig functions, or whatever. You had to search for a correct method. And the more problems you worked, the better you got at it. Well, the same type of thing happens here. This differential equation is obviously going to be separable because it's in the section of separable differential equations. But just like in Calc 2, where you look for a method of integration, and you also did this similar thing for determining a method or determining how a series converged. You had to look through multiple different methods. Comparison test, ratio test, root test, integral test, all kinds of stuff, the divergence test, and you pick the right method. The same thing goes here. Goes for your exam coming up. Okay, this is going to be separable, even though it doesn't look like it. How are we going to separate e to the x minus y? Not too rough. The same way I manipulated the exponential function in the last two examples, I can manipulate e to the x minus y. E to the x minus y is e to the x, e to the minus y. Okay, it's like using the rule a to the m plus n equals a to the m, a to the n. It's kind of maybe I'll start putting my reminders the way I did previously. Put them in some other color like green with a little reminder. Alrighty, so now we can separate the variables. So if we separate the variables, we get, if we multiply both sides by e to the positive y, or you could divide both sides by e to the negative y, but if you divide both sides by e, or multiply both sides by e to the positive y, you get e to the y dy equals x e to the x dx. The reason I chose this is as a gentle reminder that we have to remember how to integrate. So this course has Calculus 2 as a prerequisite, and as a prerequisite, as a prerequisite. So in Calc 2, one of the two big things you did was integrate. So we need to be able to integrate. So we get e to the y dy. Now, do you remember how to integrate x e to the x? Integration by parts. If you have forgotten it, you ought to look it up. I can't teach you integration by parts. I can tell you what you would do, or remind you what you would do. You would let u equal x, dv equal e to the x dx. And you get du equals dx, you get v equals e to the x. So you get uv, oops, I don't want to be in red anymore, I want to go back to black. uv x e to the x minus the integral of v du. The integral of e to the x is just e to the x again, so plus a constant. So that's what we get after we integrate. So can you see what I have a little extra of on the left-hand side? Can you see it? Right there. So we have e to the y equals e to the x times x minus 1 plus a constant. That's an implicit form of the solution. An explicit form of the solution we get by taking the natural log of both sides. So the natural log of e to the x, you don't have to factor out the e to the x the way I did. And there are no absolute values here. There's no reason for them. I didn't integrate. You got the absolute values by integrating 1 over y. When you take the natural log of both sides, absolute values don't just pop into existence out of nowhere. So no absolute values necessary, or actually no absolute values can be written here. That would just not be correct. Okay. So let me see where we want to go from here. We want to go to another example. So example. So you're seeing this section is very simple. Simple, quote unquote. The difficulty of this section is only going to be, the section's difficulty is only related to your ability to integrate. So if you're weak at integration, this section's going to be harder than if you're strong with integration. Okay. In any case, you'll be seeing enough examples to help you get up to speed with integration if you're not. So this is obviously separable. I have a differential equation in differential form. So let's separate the variables. So if we divide both sides by y squared, so we get dy over y squared equals, divide both sides by x squared plus 1. And then we integrate both sides with respect to the variable on each side. So the integral of 1 over y squared is negative 1 over y. I'm pretty sure you can probably see that, because this is like y to the negative 2 dy, which is y to the negative 1 over negative 1, or negative 1 over y. Now that gave you time to think about what goes on the right-hand side. This is 1. And I'm going to use a phrase that I use so often in my career. This is one that you should know. This is an absolute one that you should know. Don't be too embarrassed if you don't, because nobody's watching except for you. And also, a lot of students forget this one, but it is the inverse tangent. Okay, so this is an implicit form of the solution. So if we take the reciprocal of both sides, we get minus y equals 1 over inverse tangent x plus a constant. Multiply both sides by negative 1, and you get negative 1 over the inverse tangent of x plus c. Now, I'm going to ask you a real quick true or false question. True or false? The general solution can also be written as y equals 1 over some constant k minus inverse tangent of x. I'm going to save you some grief. It's true. It doesn't look like it's true. It doesn't look like it's true. It looks like, well, maybe he brought the minus 1 down. There's the negative inverse tangent. What about the constant turned into a positive? It sure did, but that's okay. I'm bringing this up for a very important reason. Your solutions may not look like the ones offered in the back of your textbook. And the reason primarily is your author juggled constants to form different forms of the same thing. So if you, different forms of the same solution. So if you take the negative 1 in the numerator and put it in the denominator, or this more technically, if you multiply numerator and denominator by negative 1, you get this. Now, c is an arbitrary constant, so replace c with negative k, another arbitrary constant. Arbitrary means it can be equal to anything, so replace c with negative k, and you get plus k. Okay, so that's the same thing, absolutely the same solution. K minus inverse tangent of x. What form do I want it in? I don't care. For the one I have in the previous, in the black versus the one I have in purple makes no difference. Be gentle on yourself. Just when you get a solution, stop. When you get a nice form of the solution, just stop. The simplest form of the solution, just stop. Okay. I want to solve an initial value problem before we dig into our next section. So example, solve the initial value problem. Initial value problem is x dy minus y dx equals 0 with y of 2 equaling 5. Okay, a differential equation with an initial condition is called an initial value problem. So solve the differential equation first. Separate the variables. X dy equals y dx. So divide both sides by xy. Divide both sides by x times y. Or you can think about it as divide both sides by y and then divide both sides by x. It makes no difference. Be careful with absolute values. Be extremely careful with absolute values. The integral of 1 over y is not the natural log of y. It's sad, but I predict, and I'm only doing this to motivate you to be very careful, but I can predict that multiple people are going to not put absolute values on the test when you do this, and you must. It's wrong without. It's wrong without. I'll say it one more time. It's wrong without absolute values. Okay, fair warning. Okay. Alrighty. So let's get an explicit solution. If I subtract the natural log of x from both sides, natural log of the absolute value of x from both sides, then I get the natural log of y over absolute value of y over x equals c, property of logarithms. Exponentiate, I get the absolute value of y over x equals e to the c. Get rid of the absolute values, y over x equals plus or minus e to the c. Y over x equals then some constant k. Remember, e to the c is just a constant. Plus or minus e to the c is an arbitrary constant. As c goes to infinity, or negative infinity, you get 0. So it goes, this plus or minus e to the c goes through all constants. If you allow e to the c for c negative infinity, you get every single constant. So y equals kx. That is the general solution. Okay, but I have an initial condition. Y of 2 equals 5. So substitute that into the solution. So y is 5 when x is 2. Okay, so that says the constant should be 5/2. So the solution doesn't have an arbitrary constant in it. It is y equals 5/2 x. Okay. So what we've done is we finished the first two sections, sections 3.1 and 3.2. We have one more to cover in this video segment. I anticipate half hour to 45 minutes, maybe, or a little bit more in this, so you may want to take a little break. I'm going to take a little break. You may want to take a little break. Mine's going to be for a few minutes, but it only feels like a few seconds. I think you ought to take a break too. So I hope you had a good break. Welcome back a few seconds later. Really, I took about a 10-minute break. Okay, let's dig into section 3.3, exact differential equations. Exact differential equations. Now, in this section, we're going to need some materials that are learned in Calculus 3. Now, even though this course only has a Calculus 2 prerequisite, we're going to use some materials from Calculus 3, and that's the bad news. The good news is the materials are very simple. I'm going to give a very short review of partial derivatives. So if you've had calculus 3, you could probably skip forward to when we actually look at the exact differential equation method. So I'm going to do a little bit of review, probably for about 5 or 10 minutes, of just partial derivatives. Okay, so if you tune in, especially if you haven't had calculus 3 yet. Now, first of all, partial derivatives are very simple. Let's look at derivatives that you learned in Calc 1. Let's take a look at not reviewing, but let's take a look at a kind of derivative that you learned in Calc 1. So suppose we look at, say, the derivative with respect to x of x squared. Can't get much simpler than that. Clearly that's equal to 2x. Now suppose we want the derivative of, say, 3x squared. We know that's also very, very simple. But the process involved actually is to assume that we can factor constants from differentiation, and then the derivative of x squared is 2x, and then we get 6x out of that. We don't usually think about it that way. We just think about bringing the 2 down and multiplying it by 3 to get 6x. But this is really what's going on. Now suppose we have something like the derivative with respect to y of y cubed. That's 3y squared. Okay, oops, that's the sloppiest 3 today. Okay, that's 3y squared. So suppose I want the derivative with respect to y of something like 4 times y cubed. This means 4 times the derivative of y cubed. Okay. Constants can be factored from the differentiation operator, or operation if you want. So 4 times 3y squared, or 12y. Okay. Now what I want to assume in this next derivative is that x and y are both independent variables of some function. Okay, in other words, I want to assume that I have a function, capital F, of x and also of y. If you've had Calc 3, this is no big deal. If you haven't, we can have functions of more than one variable. And I want to make that function y cubed times x squared. Okay, so for this function, x and y are both independent variables. That means y does not depend on x. Y is not a function of x necessarily. Okay, so if I do that, I can consider another kind of derivative. Now I'm gonna draw a stylized d. Looks like a backward 6. Very often it's called a lyrical D, because it looks very kind of like the D would be used in writing poetry. It's kind of sweeps and is attractive looking D, but it really is a curved D, a curly D, if you will. It looks like a backward 6, but it's supposed to remind us of a D. And I'm going to use that symbol again to write not d over dx, but this symbol over this symbol over this symbol x. This and then I'm going to write of y cubed x squared. This means I'm taking the derivative with respect to x, just like before with the regular d. It means a derivative with respect to x, but it also means that I'm holding every other independent variable. There's only one other independent variable. Every other independent variable constant. That means I'm taking the derivative with respect to x and I'm holding y constant. So if y is constant, then y cubed is constant. That means that I can factor out the y cubed from this differentiation operation, just like I did with the ordinary differentiation operation, and then take the derivative with respect to x of x squared is 2x. So we get 2xy cubed. This has a special name. This is called the partial derivative. Partial derivative of y cubed x squared with respect to, oh my goodness, I suppose I wrote the words respect to as one word, with respect to x. Okay. Similarly, I could take the partial derivative with respect to y of y, the same function, y cubed x squared. Okay, what that means is I'm holding every other independent variable. In this case, again, there are only two independent variables, x and y. I'm holding every other independent variable, namely x, constant, so it can be factored out of the differentiation operation. And then I take the derivative of y cubed with respect to y. This is nothing more than 3y squared, or 3x squared y squared. This is the partial derivative with respect to y. The partial derivative with respect to y. And notice the partial derivative with respect to x and with respect to y are very different. They're not necessarily, in fact, most generally, they're different. They're not necessarily equal to each other. Okay. So now let's do this again, but go a little further. So let's let f of x and y equal 3x squared y squared. Okay. So oh no, sorry, I don't want 3x squared. I want the original function. Let's let f equal y cubed x squared. Sorry about that. Y cubed x squared. So far I have the partial derivative of f. The partial derivative of f with respect to x is 2xy cubed. I also have the partial derivative of f with respect to y is, remember, I'm holding x constant, 3x squared y squared. 3x squared y squared. We did that. Okay. Now the reason I'm doing this again is that we have higher order derivatives. I can take another derivative. I can take the partial with respect to x of partial f partial x. And just like with ordinary derivatives, this gives me the second partial derivative of f with respect to x, partial squared f over partial x squared. And that means I take the derivative with respect to x again. Well, if I take the derivative with respect to x again, that means I hold y constant. Okay, now concentrate on what I just said there. 2 is constant, y cubed is constant, so the only thing that's variable is the x, and the derivative of x is 1. The derivative of x is 1, so this is nothing more than 2y cubed. Okay, so let's take the second partial derivative of f now with respect to y. So holding everything else besides y constant, namely x. 3 is a constant. X squared is a constant. When I'm taking a derivative with respect to y, the x is constant. Anything with x in it is going to be constant. So this is nothing more than the original 3x squared times 2y. Derivative of y squared is 2y, or 6x squared y. Okay. Now here's where it gets different from calculus 1. Back to the partial derivative of f with respect to x. That is 2xy cubed. Okay. Now, the partial derivative of a function of two variables, x and y, or three variables, or four variables, or whatever, but a partial derivative of a function of two variables with respect to x is another function of two variables. The result, partial f partial x, is 2xy cubed. It's another function of x and y. So I could take another derivative with respect to x. I did that. I did that right here. But I could take another derivative not with respect to x, but with respect to y. I'm going to do that in red here. I can take the partial derivative with respect to y of the partial derivative of f with respect to x. Okay, so we never had anything like this in Calc 1. Because in Calc 1 we only have functions of one variable. So let's see what happens if I take another derivative of the part of this function, but now with respect to y. This is called a mixed partial derivative. This is called a mixed partial derivative. Mixed partial derivative. Derivative. Mixed partial derivative is when you take the partial derivative with respect to one variable and then take another derivative with respect to another variable. Okay. And what we're going to get is the second partial derivative of f. Now here's where you have to be real careful with the symbols. And you could rewrite the symbols just like they would be if you were multiplying. It's first with respect to x, just like you're multiplying the red partial y with the black partial x, but it has to be in this order. This is read from right to left. The partial derivative with respect to x, then with respect to y. Then we take the partial. What's the partial derivative of 2xy cubed with respect to y? That means the only live variable quantity is y cubed. And what's the derivative of y cubed? It's 3y squared. Y squared. X is held constant, so this is 6xy squared. I'm going to do the same thing with the partial derivative of f with respect to y. So the partial of f with respect to y was 3x squared y squared. That was way up here, way up here. 3x squared y squared. I'm just going to copy it down again. 3x squared y squared. Okay. 3x squared y squared. Now I'm going to take the derivative of both sides with respect to x. I'm going to take the derivative with respect to x of both sides, forming another mixed partial derivative. Okay. 3x squared y squared. So let's combine the symbols. On the left we have partial is partial squared, partial y first and then partial x second, reading it from right to left again. Now let's take the derivative with respect to x of 3x squared. Remember, y is held as constant, so the derivative of actually it would be just of x squared. The derivative of x squared is 2x. So we're going to get 6xy squared. Okay. Notice that the two mixed partial derivatives, the second partial with respect to x first, and then with respect to y second, is the same. It's equal to the second partial first with respect to y and second with respect to x. They're equal. For all of the functions that we're going to be dealing with, this is always true. This is always true. Mixed partial derivatives are equal. Mixed partial derivatives. So let's abbreviate this. Mixed partials means partial derivatives are equal mixed partials, mixed partial derivatives, mixed partials are equal the second derivative of f first with respect to x and then with respect to y is the same thing as the second derivative of the function first with respect to y and then with respect to x for every kind of function that we're going to deal with. Okay. Those of you who've had Calc 3, you're probably bored solid with this because this is something you learn in Calc 3 and in Chapter 14 of our textbook. Okay. Bear with me. We're almost ready to continue with our differential equations. Okay. Now, just to be really complete about this, remember how in calculus you have a symbol dy dx, and you can abbreviate that y prime. Well, we have a similar situation with partial derivatives. Partial f partial x can be written as f sub x. Partial derivative of f with respect to y can be written as f sub y. So, how would we write the mixed partial first with let's do a simpler mixed partial. Mixed partial of f with respect to x. It would be fx x. Just like you have the second ordinary derivative of y with respect to x is y prime, double prime. Okay, just to be complete, second partial derivative with respect to y would be fyy. So, I wanted to get to this one. The second partial, how would we write second partial first with respect to x and then with respect to y? We would write it f x y. It's a little quirky thing with the notation is with the curly d notation in the denominator of the curly d, you have to read from right to left. But with the subscript notation, you'll read from left to right. So first, second, first, second. Okay. So what's fyx? It's the second partial. Get rid of these little twos and ones. It's the second partial derivative. That's the easy part. First with respect to y, then with respect to x. Okay. So let's get to our section. Let's get to section 3.3. 3.3 starts now. We needed the partial derivatives to be able to do this. Alright. So, we want to solve another kind of differential equation. Let's assume that x squared plus y squared equals 4. Okay, so we have an equation, x squared plus y squared equals 4. Now we're going to use a little Calc 3, but we can probably get away with using Calc 1 to do this. Let's let w equal x squared plus y squared. Okay. Now, this is where the Calc 3 comes in. If you haven't had it, don't worry about it. You won't need this with the method of solution. Now, w is a function of two variables, x and y. If you're wondering, and if you've had Calc 3, we're going to be using the chain rule from Calc 3 to do some stuff. And again, if you haven't had Calc 3, just bear with me. You'll be okay. I'm just motivating the method here. Basically, you just remember the method. You don't have to have the background, the derivation background. Okay, this is just to help. I would rather you understood, but if it's okay if you haven't had Calc 3. So, w is a function of x and y, where x is a function of itself, and here I'm going to assume that y is a function of x. Okay, so we could write y equals the square root of 4 minus x squared, plus or minus. But I'm going to isolate one function. If I solve for y, I would have y as a function of x. So this new function w still equals 4. X squared plus y equals 4. But the w is a function of x and y, and each of x and y are both functions of x. X is a function of itself. It's just itself. And y is a function of x. Okay, I'm assuming that I can solve for y. So by the chain rule, then the derivative, ordinary derivative of w with respect to x, ordinary derivative by the chain rule is, now if I call this x squared plus y squared the function capital F, then the chain rule says it's partial f, partial x. If you remember, you go down the direction of the first x, then you keep going down the derivative of the branch that leads to the end times the derivative of x with respect to x, plus then we take the branch that goes in the other direction. So to go from f, capital F, to y, we take the partial derivative of f with respect to y. Then we go from y to x by an ordinary derivative times dy dx. And remember, this is w equals ultimately 4, and so the derivative of 4 is 0. So what this leaves us with is partial f with respect to x. Well, what's the partial derivative of x squared plus y squared? It's 2x. Partial derivative of x with respect to itself, plus the partial derivative of f. Remember, f, the function capital F, is x squared plus y squared, and the partial of that with respect to y is 2y times dy dx equals 0. Okay. If you wanted to think about this just using Calc 1, you could kind of get away with it. You can kind of get away with it. See, w equals x squared plus y squared. You can get away with it using implicit differentiation. Implicit differentiation. Derivative of x squared is 2x. Derivative of y squared is 2y prime. Okay. And no matter how you think about it, in any case, if you multiply both sides by dx, you get 2x dx plus 2y dy equals 0. Now, what happened was this. I ended up with a differential equation. What happened was this. I started with x squared plus y squared equals 4. I started with the solution to the differential equation, and then I derived the differential equation. Our task is to go backwards. Okay? We want to go backwards. We want to go backwards from this. We start here. Start with a differential equation. And go backwards, and get that's the solution, the implicit solution. Okay, so I want to reverse these steps. Okay. So here's how the general case goes of what I just did. Okay, suppose we have Suppose we have w equals some function x of x and y equals a constant. Just like before, I had w equals x squared plus y squared equals 4. Okay. Then, with the help of a little bit of Calc 3, the function capital F is a function of x and y. X is a function of itself, it just equals x, and I'm assuming that in this function of x and y depends on x. I have an some function y of x, theoretically. Okay, so using the chain rule from Calc 3, bear with me, people who haven't had Calc 3. You don't have to do this. You won't have to do this in the method. You have the partial of f with respect to x times the derivative of x with respect to x is 1, plus the partial of f with respect to y times, oops, did you catch my mistake with the chain rule? Y is a function of x. The partial of f with respect to y times dy dx equals the derivative of w. See, this is what I'm finding. I'm finding dw dx. Derivative of constant is 0. So that gives me this. If I multiply both sides by dx, partial f partial x dx plus partial f partial y dy equals 0. And I want to go backwards. I want to start here. I want a method that's going to allow me to start right here and go backwards to the solution that will look like what we started with. Here I started with the solution and used the chain rule to get a differential equation. I want to start with the differential equation. Now the differential equation is not going to look like, it's not going to have partial derivatives in it. It's going to have some function of x and y times dx plus another function n of x and y dy equals 0. I mean, this is how our differential equation is going to be given to us. M dx plus m dy equals 0, where m and n are functions of x and y. Before we even get started, we need to make sure that that m and that n are derivatives of some master function, solution function, f. First one with respect to x, first coefficient with respect to x, second with respect to y. If you didn't catch what I just said, it's kind of complicated. We need to make sure, and it's not always going to be the case, but we need to make sure that there exists some function, f such that that m is the partial derivative of that function with respect to x, and that n is the derivative of that same function with respect to y. It does not necessarily have to be the case that the differential equation will be, that we can even go backwards from what I have above. We can only go backwards if those coefficients of dx and dy are partial derivatives of the solution function. Okay? If there does exist a solution function, if there is a solution function, we'll call it solution function f, then the differential equation is called exact. If there doesn't, then it's not exact, and you can't use this method. So we need some sort of test for exactness. How are we going to be able to determine that there is such a function? Okay. So, I want you to notice something. I want you to notice a lot of things, I guess, but I want you to notice, if the partial derivative of f with respect to x equals m, and the partial of the same function f with respect to y is n, then let's take some mixed partials. Let's take the mixed partial of the first one with respect to y. It's already with respect to x. Now let's take the derivative of both sides with respect to y. That's going to be partial of m with respect to y. And let's take the second the second equation, the partial of f with respect to y equals n, and let's differentiate both sides of it with respect to x. It's already with respect to y. Now let's take the derivative with respect to x. It's going to be the partial of n with respect to x. Notice that these are mixed partials. These are both of the mixed partials. And what happens with mixed partials? They are equal. So the partial of m with respect to y equals the partial of n with respect to x. It turns out that these steps are reversible. That's the key. It turns out that what I just did in this note is reversible. So if the partial of m with respect to y equals the partial of n with respect to x, then there exists a function so that the partial with respect to x is m and the partial with respect to y is n. Now, if you're getting lost in all this, relax. What I've been coming up with is the test for exactness, and there's a bottom line here, and this is for everybody, whether you've had Calc 3 before this or not. It's Theorem 3.2, and it's the test for exactness. Test for exactness. Yes. So here it is. Differential equation m of xy dx plus n of xy dy equals 0 is exact if and only if, and here's the test, the partial derivative of the first coefficient with respect to the other variable is equal to the partial derivative of the second coefficient function with respect to the first variable. Okay, if that's true, the differential equation is exact. Then you could use the method that I haven't shown you yet for going backwards and getting the solution. So here's the method for solving exact differential equations. It's not difficult. Now, another fair warning for your exam: don't use methods from other textbooks or other websites to do the problems, any of the problems, from any problems on any test, but specifically any problems for exact differential equations. Don't use other materials. Do it this way. Okay? Fair warning. You will not get credit on work on your exam using materials from other websites, methods from other websites. I'm very explicit about that in my directions, but I wanted you to hear it one more time. Okay, with that said, let's discuss a method for solving exact differential equations. Suppose you want to solve sine of y dx plus x times cosine of y minus 2y dy equals 0. This is a differential equation, first order differential equation in differential form, and it's not separable. There's no way you can separate x's and dx's from y's and dy's. You just can't do it. Can't be done. Okay, so m equals sine of y, n equals x times cosine of y minus 2y. I just realized something. I just realized my air conditioner's on. I'm trying to turn it off while lecturing. I'm sure this is real loud, so I'm going to take a break for a second and turn that off. My apologies, students. This recording is taking place at the end of a very hot summer, and I'm trying to start with a cool room, then turn off the air conditioner while I record, and then take a break and turn it back on again. So Anyway, it's a little too much information, but if you notice, if the AC was rattling, it's not the video, it was my AC. Okay, so back to our differential equation. M equals sine of y, n equals x cosine y minus 2y. The first thing you need to do is test for exactness. Test for exactness. Test the differential equation for exactness. Okay, so the partial derivative of m with respect to y, the partial derivative of the coefficient of the dx with respect to the other variable y is cosine of y, cosine of y, and the partial derivative of n with respect to x, what's the derivative of x times cosine of y with respect to x? So y is constant with respect to x, so cosine of y is constant. So the only live variable is x. What's the derivative of x? It's 1. So the derivative of x cosine of y is just cosine of y. What's the derivative of 2y with respect to x? It's 0. Because when you take a derivative with respect to x that you hold y constant, the derivative of a constant is 0. In any case, the partial derivative of m with respect to y equals the partial derivative of n with respect to x. So the differential equation is exact. So how are we going to solve this differential equation? So we know that the partial derivative of my solution function with respect to x is the coefficient of dx. It's sine of y. There exists a function f. So the partial derivative of f with respect to x is sine. The partial derivative of f with respect to y is the other coefficient, is n, is x cosine y minus 2y. So here goes the method. Take the first derivative here, the partial with respect to x, and integrate both sides with respect to x. Integrate both sides of this differential equation with respect to x. So the function then is the integral of the derivative with respect to x. We integrate that with respect to x, so it's the integral of sine of y with respect to x. Now here's where it gets a little tricky for students who haven't had Calc 3, even for students who've had Calc 3. This integration is not regular integration, it's partial integration. We're doing the opposite of taking the partial derivative with respect to x. We're integrating partially with respect to x. That means we're going to integrate pretending that y, or anything that has an y in it, is constant. So if y is held constant, then the sine of y is constant. What's the integral of a constant with respect to x? It's just x times the constant. So this is x times the sine of y plus the constant of integration. Now, it gets a little trickier here with this constant of integration. It's not just plus c. It's not just plus c. We're integrating with respect to x. That means we're holding y as constant. So the constant of integration will not be a constant. It will be any function of y. I'll justify that again in a minute. So this constant of integration is not a constant. I'm going to put it in quotes, constant of integration. It's not necessarily constant. It's a function of it's a function of the variable that was held constant. Now, if you're not sure if this is correct, take the derivative of this function with respect to x and see what happens. The partial derivative of this function with respect to x is, well, what's the derivative of x times sine of y with respect to x. It's sine of y. Now here's where you can understand why the constant of integration is really a function of integration with the variable opposite the variable of integration. What's the derivative of any function of y, h of y, with respect to x? It's 0, because y is held constant. So anything with y in it is constant. I could have put cosine of, I could have put the function of the solution already has cosine in it. I could have put log of y, or e to the y, or sine of y squared. What's the derivative of all these functions of y with respect to x? Is 0. Okay, I'll get rid of that. So when you integrate partially with respect to x, the constant of integration is an arbitrary function of y. Okay, that's an important thing here. All right, so now we're not done, because our solution doesn't have a function of y, an h of y in it. We need to figure out what h is. So what have we not used yet? We haven't used the fact that the partial derivative of my solution function with respect to x, with respect to y, is x cosine y minus 2y. So take the solution that we have so far by integrating with respect to x and differentiate that with respect to y and see what happens. The derivative of sine of y is cosine of y. The derivative of h prime, the derivative of h of y with respect to y is h prime of y. What does that have to equal? Well, it's right up there. This must equal to, so we set this equal to x cosine of y minus 2y. Now look what happens when we subtract x cosine of y from both sides. We get h prime of y equals negative 2y. So integrate both sides with just regular integration with respect to y on both sides. You get minus y squared plus some constant. So the answer is, remember we were going backwards, f of x, y equals some constant of integration. Constant. Let's say I want to use k for the constant that I just got in h. So the solution is f of x, y. Well, what's f of x, y now that we figured out h? F of x, y is x sine of y plus h of y. Then the solution then is x sine y minus y squared plus some constant k equals a constant. I'll combine those two constants. The solution then is x sine y minus y squared equals, say, a constant c. Okay. It seems like there's a lot more going on in this solution than there really is. Let's take a look at another example. Okay, let's see here. Get one that's not too rough. Let's see. Okay, I'm going to keep them kind of simple at first here. So, oops. Example. Solve 1 plus y squared dx plus 2 times x plus 1 y dy equals 0. Now notice here, this differential equation is separable. This differential equation is in fact separable. We could solve this by separating the variables. So sometimes you can use multiple methods for solving these differential equations. Okay, so first, test for exactness. So the partial of the first, partial of the coefficient of x, but the partial of that with respect to the other variable y is 2y. The partial of the other one, the coefficient of y, the partial of that with respect to x, well, what is this function if you were to distribute everything? You get 2xy plus 2y. So what's the partial of that with respect to x? The partial of 2xy with respect to x, the derivative of x is 1, so it's just 2y. And what's the partial of 2y with respect to x? It's 0. So partial m with respect to y equals partial n with respect to x. To solve the problem. Equation is exact. So there exists a function f such that the derivative of the function we're looking for with respect to x is 2y, and the derivative of the function we're looking for with respect to y is the other, oh, sorry, it's not 2y. that's the derivative. The partial of f is 1 plus y squared. Partial with respect to x is 1 plus y squared. That was a really bad blunder. And the partial with respect to y is the simplified or non-simplified 2xy plus 2y. Let's see, 2xy plus 2y. Now we can go backwards with those partial derivatives to get the original function. So take the partial with respect to x and integrate both sides with respect to x. So f equals the integral of 1 plus y squared with respect to x. Okay. That integral with respect to x is very, very simple. What's the integral of 1 with respect to x? It's x. What's the integral of y squared with respect to x? Well, y squared is constant with respect to x, so it's y squared x. You integrate with respect to anything, you get a constant of integration. But we're integrating with respect to x, so any function of y will do perfectly well as this sort of quote-unquote constant of integration. So that's my solution function. Now what I haven't used yet is the fact that the derivative of my solution function with respect to y is 2xy minus 2y. So take the function that I have so far and take the derivative of that with respect to y. So the first thing to do is to integrate the partial with respect to x with respect to x, integrate it with respect to x, then differentiate it, that result with respect to y. Every time, every single time. Okay, so the derivative with respect to y of x is 0. The derivative of y squared is 2y, x is constant, plus h prime of y. And that must equal, so we set it equal to 2xy plus 2y. So h prime of y equals 2y. Integrate that little equation with respect to y, and you get h of y is y squared. So the function f must equal x plus y squared x. You can say y squared plus a constant. I forgot the integration constant. X plus y squared x plus y squared plus a constant equals another constant. So combine the two constants and you get a solution, x plus y squared x. The first one's constant 1, the second one's constant 2. So x squared plus y squared x plus y squared equals a combined constant. Okay, and that's your solution. Okay. I think that these two these two problems will be a good model for you, or good models for homework. They all go the same way. They all go the same way. You take you first test for exactness, and then you use this procedure of basically integration to reconstruct the solution. Okay, so that ends our video segment, kind of a long video segment this time. Covered 3 sections, 3.1. Nothing for you really to worry about, other than just definition of what a differential equation is, what a solution is, and what an initial value problem is, and what solutions to them look like. And then we dig into 3.2 and 3.3 with the first of several more solutions to mostly for first order differential equations for chapter 3. So as usual, I am looking forward to talking with all of you again very soon.